All right, today we're going to learn a new language. Now, it's not one you speak, but it's one that scientists all over the world understand. It's the language of organic chemistry, a system that lets us turn these really complex looking chemical names into precise visual blueprints. So let's just dive right in. So here's our game plan. First, we're going to figure out why on Earth we even need a universal naming system. Then we'll get to know the simplest organic molecules and learn the different ways chemists, sketch them out. After that, we'll kick it up a notch with something called functional groups, learn the actual rules of the road for naming, and finally, we'll put it all together to crack that chemical code that looks so intimidating at first. And speaking of intimidating, take a look at this. Right now, this probably looks like absolute gibberish, right? A total mess of numbers and letters. But I promise you, by the end of this, you're going to see that it's not random at all. In fact, it's a perfect, logical set of instructions for building one specific molecule. So why do we need this whole system in the first place? Well, the answer really comes down to one single element: carbon. It's the absolute star of organic chemistry. Its unique properties let it form an almost unbelievable number of different molecules. You see, carbon's special trick is that it's amazing at forming strong bonds with other carbon atoms. This means it can build these long, straight chains, or these really complicated branch structures, or it can even loop back on itself to form rings. And since every carbon atom always forms 4 bonds, the number of possible combinations is, it's practically infinite. Without a system to name them, it would just be pure chaos. When you learn a new language, you don't start with complex poetry, right? You start with the simple words. And in organic chemistry, that means starting with the simplest family of molecules there is, the hydrocarbons. They are the absolute foundation. The definition is right there in the name: hydro for hydrogen and carbon for, well, carbon. But the most important word on this slide, the one you really got to remember, is only. If there's even one other atom in there, say an oxygen or a nitrogen, it's not a hydrocarbon anymore. The definition is super strict. And inside that hydrocarbon family, the simplest of the simple are the alkanes. Think of them as the basic skeletons of the molecular world. They're just chains of carbon atoms, all hooked together with single bonds, and every other spot is filled up with a hydrogen. No bells, no whistles, no double bonds, just pure, simple structure. This table shows you just how logical this whole system is. This is what we call a homologous series. Just look at the pattern. Methane's got 1 carbon, ethane, 2, propane, 3. And every time we add a carbon, we add 2 hydrogens. See? The names and the formulas follow this beautiful, predictable rule. And that's the whole point. Okay, so before we can properly name these things, it really helps to know how we're supposed to draw them. Chemists have a few different ways of sketching out the blueprints for these molecules, ranging from showing absolutely everything to a super clean, simple shorthand. First up is the displayed formula. This is the show everything model. You see every single atom and every single bond holding them together. And for small, simple molecules, this is great. It's incredibly clear. But as you can imagine, it gets really cluttered and messy fast once the molecules get bigger. So, to clean things up a bit, we have the structural formula. This is a much neater shorthand. Instead of drawing every single carbon to hydrogen bond, you just group the hydrogens next to the carbon they're attached to. It's kind of like condensing a long, wordy sentence while keeping all the critical information. And then we have the expert's secret code, the skeletal formula. Honestly, this is the cleanest, fastest way to draw a molecule, and it's what you'll see most often. With this style, every corner and every end of a line is a carbon atom, and the hydrogens, they're just implied. We know they're there because every carbon has to have 4 bonds. It's just sleek and super efficient. Okay, we've got the basic skeletons down. Now it's time to add a little personality. The parts of a molecule that are responsible for most of the interesting chemistry, the parts that give it character, are called functional groups. So a functional group is basically the active part of the molecule. It's a specific little cluster of atoms that totally defines how that molecule is going to behave. For instance, if you slap an OH group on a chain, boom, it becomes an alcohol and it acts like an alcohol. Add a COOH group and now it's a carboxylic acid and it's acidic. These groups are everything. They dictate the molecule's identity. All right, so let's recap. We've got our basic vocabulary, the carbon skeletons, and we have our key descriptive parts, the functional groups. Now it's time to learn the grammar that holds it all together. Let's get into the actual rules for building a proper chemical name. The absolute foundation of any name is its stem, and the stem just tells you how many carbons are in the main chain. 1 carbon is meth, 2 carbons is eth, 6 is hex. Seriously, memorizing these first few is like learning your ABCs. It's the alphabet of organic chemistry. So, the whole naming process really just boils down to these 3 core rules. First, you find the longest unbroken chain of carbons you can. That gives you the parent name. Second, you look for any branches hanging off that main chain. A 1-carbon branch is a methyl group, a 2-carbon one is ethyl, and so on. And finally, and this is crucial, you number the carbons in the main chain so that the branches have the lowest possible address numbers. That rule ensures every name is totally unique. Okay, this is it. This is the moment we've been building up to. We've learned the alphabet, we've learned the grammar, it's time for the payoff. Let's go all the way back to that crazy-looking name from the beginning and see if we can crack this thing wide open. Here we are, 2,5,5-trimethylhextuene. Doesn't look nearly as scary now, does it? You can actually start to see the different parts. It's not just a random jumble of letters and numbers anymore. Now we have the tools to translate it. Let's start from the back and work our way forward, because that's where the main chain info is. Hex, that tells us the longest chain has 6 carbons. Easy. The ene ending tells us there's a carbon-carbon double bond somewhere in that chain. And the 2 in the middle, that's the address. It tells us that double bond starts on carbon number 2. See? Each part is a specific instruction. Now let's look at the front part, which describes all the branches. Methyl tells us the type of branch. They're all single carbon groups. Tri tells us the quantity. There are 3 of them. And the numbers, 255, well, those are just the street addresses. They tell us exactly where those methyl groups are located, 1 on carbon 2 and 2 of them on carbon 5. Every single piece has a job to do. So, when you put it all together, you realize that this long, complicated name, it's not just a label. It's a complete, precise set of instructions. It's a recipe that any chemist anywhere on the planet can follow and end up drawing the exact same unique molecule. And that is the absolute key takeaway. This system isn't designed to be confusing jargon to keep people out. It's designed for perfect clarity. Each name is a unique molecular blueprint containing every single piece of information you need to build the structure from scratch. Look, we've really just scratched the surface today, but you now have the fundamental tools to start decoding the language of organic chemistry. And this is so much more than just a naming game. It's the foundation for understanding the molecules that literally make up our world, from medicines to plastics to us. So now that you can read the blueprints, what are you going to build?